Great. Well, thank you so much for the invitation. And yeah, hopefully in time I will be able to visit in person. So the talk is on generalized energy-based models. The co-authors here are Michael Abel and Jan Jo, who are responsible for all the hard work of this paper. I should say as well, like, I'm not sure what the protocol is for questions, but I'm happy to actually take questions throughout the talk. I have the chat window open, so if people prefer to type a question in chat, they can do that, or unmute and ask. I'm happy either way. And of course, I imagine there's also some time to take questions at the end. Great. The topic is generalized energy-based models. So the goal here basically is the goal of generative modeling, which is that given a collection of samples, I'm going to call X here from an unknown distribution P, I want to generate samples Q. So Q are my artificial samples that in some sense resemble P. All right. And the sort of, shall we say, theme that we pursue here is that these samples are in very high dimensions, but might occupy a low dimensional subspace in some sense within that high dimensional space. So for example, here we have the task of generating pictures of bedrooms. On the left, we have example photographs of bedrooms. On the right, we have artificially generated samples of bedrooms. And a goal of generative modeling is to train our artificial generator Q so that it generates samples that resemble the target samples P. And this is a distribution matching task. So it isn't that we want our Q to generate a single really good picture of a bedroom. Like, that would be easy because I just take one of the photos and reproduce it. I want to cover the set of possible bedrooms. So I want to generate samples that span in some sense the space of bedrooms and generate some more likely bedrooms more often than other less likely bedrooms. So to train a generative model in this way, the key ingredient is a divergence measure. So some measure of difference between the set of real bedrooms as shown by this distribution P and the set of synthetically generated bedrooms from this distribution Q. So I need in some sense a loss function for my generative model, where the loss function is telling me how close Q approaches P. Now, one of the most popular model methods for generative modeling are generative adversarial networks. And this is the foundation on which I'm going to be building this talk. So it's worthwhile to remind everyone in a cartoon form what this setting is. So in a generative adversarial network, I have a generator here shown as a student, a little artist, who is given a task of generating a set of objects to match a target set. So in this case, the task is that the generator should generate a set of synthetic dogs. And then I have a critic, the critic being my D function from the previous slide, which takes the set of synthetic dogs, compares it with a set of real dogs, and then tells me how far apart these sets are and gives feedback to the generator. And then, the process cycles. So the student generates a better set of dogs. The critic gives feedback as to how closely that set resembles the target set. The cycle continues until either the student stops improving or the critic can no longer tell the real set from the fake set. What you'll notice here, though, which is a little bit the key point, is that after training is complete, then the critic has no more say in the process. So the student goes out into the world and generates dogs, but the information that the critic knows about how the student's dogs still differ from the real dogs is lost, right? The critic just is left alone, and the student is generating the dogs as best the student can. And this seems a little bit wasteful because unless the student has absolutely perfectly nailed the task, it's quite likely that the critic still knows differences between the real and the fake dogs. And an improved generator could actually use this information, could take this critic and say, can you help me to improve my samples even further? So this, at a high level, is the purpose of this talk. It's like, how do I take my critic and how do I use my critic to improve my samples further? How do I incorporate my critic into my sample generating process rather than just using it as a training loss and then throwing it away? So that is today's talk. All right. So now we know the theme of the talk, the purpose of the talk, a quick overview of the structure. I'll first talk about critics in a little more detail and the mechanisms that one uses in training them, I'm going to focus on a particular subcategory of critics, which are the phi divergences or F divergences, because these are the critics I'll be using downstream in my model. And in this category of critic, an important thing is to understand, in a sense, like how it is that these critics are applied in the GAN setting. So one doesn't simply take off the shelf a phi divergence and apply it. We actually use an approximation to that phi divergence that ends up having better properties than the original divergence itself, which is a little bit interesting, right? You would think, okay, an approximation is always worse than the original function. In our case, the approximation is better, and it's better in a sense that is extremely important for GANs to work and for our own model to work. Once I've gone over our critic functions, and in particular the critic functions we're going to care about, then I will talk about how to incorporate these critics into the modeling task. So how to improve your GAN. And the key message is that, like, if I have a GAN, if I have a critic and a generator, then all else being equal, incorporating the critic will always improve over the generator alone. So in every GAN, I have a generator and a critic. And my statement is that throwing away the critic is always worse than using the critic. And we're going to see how that applies in this talk. So we should keep it, we should use it as part of our generating process rather than throwing it away. All right. Okay, so let's talk about divergence measures. So critic functions, divergences, differences in probability distributions. So divergence measures live in two different sets depending on how they observe the probability distributions that they're comparing. So if I have P and Q, my set of real bedrooms, my set of fake bedrooms, and I want to compare them, there are two things I can do. I could take their difference, and if their difference is 0, then P and Q, I would conclude are the same. Or I could take in some sense their ratio P to Q. And if this ratio is in some sense 1, then P and Q are the same. Okay, so these are two fundamentally different ways of looking at a comparison of two distributions. Either I can think about their difference, or I can think about their ratio. And these give rise to two fundamentally different classes of divergence measures. So the difference philosophy gives rise to the integral probability metrics. The ratio philosophy gives rise to the phi divergences. So if we look at the integral probability metrics, we look for a function in a class of functions such that we maximize the difference in expectations under P and Q. Okay, so I'm going to show this graphically in a moment, but the fundamental principle here is that I'm looking at some witness of the difference of P and Q, P minus Q. For the phi divergences, I take the expectation of a convex function of the ratio of P to Q, and this function phi here takes a value 0 when the ratio is 1. So for this, I need P and Q to have densities. I need the ratio of P to Q to be well defined. Hold that thought because it's going to come back very shortly and get us into trouble. And then we're going to take the expectation of that phi of this ratio. So this is a lens, so to speak, that we use to observe this ratio P to Q and discover whether it's 1 everywhere or whether it's not. And if it's 1 everywhere, then I conclude that P and Q are the same. Okay, so let's spend a little bit of time, but not too much, on this side, on the integral probability metric side, before returning to the phi divergence side. Okay, so Wasserstein distance is one very popular class of critic measures for distributions P and Q. What is the class of well-behaved functions that a Wasserstein distance uses? It uses the class of functions whose Lipschitz norm is upper bounded by 1. So I'm saying, like, find me within all of the functions whose Lipschitz norm is upper bounded by 1, the function that maximizes the difference in expectations under P and Q. Okay, I'm illustrating this here with a simple example where I've got P, a set of points here, Q, a set of points there. And here is one of the functions in this class which maximizes the difference in expectation. And here is the W1 distance between P and Q, the Wasserstein distance, which is 0.88. Okay. And what we notice is that as the red points approach the blue, W1 drops, decreases. So I am giving a useful signal to my generator that my red points are improving. My red points are approaching my blue points. So in this sense, the Wasserstein 1 distance is a helpful divergence measure. It's telling me, as my red approaches my blue, that my sample generation mechanism is improving. So I'm showing this in cartoon form here as a helpful professor who is giving me constructive feedback that my quality of samples is improving. Now, another set of integral probability metrics are the maximum mean discrepancies. So a maximum mean discrepancy uses as its witness function class the RKHS functions in a sufficiently rich RKHS, so it's called the characteristic RKHS, but I won't talk about it further, whose norm is less than or equal to 1. So this is a smoothness enforcing norm in a similar way that the Lipschitz constraint on the Wasserstein 1 distance was a smoothness enforcing norm. And again, I'm looking for a smooth function which maximizes the difference expectation under P and Q. All right. And once again, for the class of functions that I've chosen for this illustration, this is a helpful critic class because as my red approaches my blue, MMD is dropping. So it starts at 1.8, it goes down to 1.1. So I have a constructive critic here. Here, though, I have to be a little bit careful because I may choose an RKHS with a richer class of functions, including less smooth functions. And if I do that, I might get a less helpful class of divergences. So here's an example where I've used, again, an RKHS with a characteristic kernel, but I've chosen my kernel to be much narrower. Now, in this case, the MMD, again, it's not that it doesn't drop as red approaches blue, but it drops by such an infinitesimal amount that the feedback that my student is being given is not very constructive. So I'm not giving like a very good gradient signal to my student as my red approaches my blue. All right. So in cartoon form, I'm showing this as an unhelpful teacher. So the unhelpful teacher is one that whatever you do, unless it's perfect, they just yell no at you. And so obviously, like as a way of giving feedback to a student, this isn't very constructive. And so it's unlikely my student is going to be improving. So I need to be a little bit careful if I'm using an MMD that I don't use too rich a function class, which includes very non-smooth functions, because in this case, I can tell that my blue and my red are wrong, but I'm not giving useful feedback to my student so that it can improve its red and move it towards the blue. All right. So these are the integral probability metrics. Now, let's spend a little bit of time on the phi divergences. Okay, so these are the divergences who use as their way of observing P and Q, not the difference of P to Q, but the ratio of P to Q. So the phi divergences include Hellinger, KL, reverse KL, chi-square, Jensen-Shannon, and various other divergence measures. Okay, so just recall from the previous slide, the definition of the phi divergence or F divergence is this function phi of the ratio of P to Q integrated over Q. And phi, as I've said earlier, is convex, it's lower semi-continuous, and phi of 1 is 0. So when the ratio of P to Q is 1, I return 0. So here's one you've certainly encountered, which is the KL divergence, and that uses as its phi u log u, all right? So if I use as my phi of u log u, which is indeed a convex function, then I recover my KL, which is integral over P of log P on Q. Okay, so KL divergence. And the KL, by the way, is the one that I'm going to be focusing on in this talk for the most part. So this is a critic function, it's a valid critic function, but is it a helpful critic function? So arguably, the KL is actually a very unhelpful critic function. It's almost like a pathologically unhelpful critic function. And the reason for this is that if the support of P and Q is disjoint, so unless P and Q occupy the same support, then the KL divergence is infinite, right? So let's say that my red, my fake samples are here, my real samples are there, and let's say that the support of my distribution of fake samples and my support of my distribution of real samples have no overlap, okay? Then KL is infinite. And KL is infinite even as my red approaches my blue. It stays infinite. So this is, in a sense, the worst possible teacher. This is a teacher that, basically, in most cases, is just going to yell no at me and is not going to give me any information whatsoever about how I might improve. And obviously, this has been known for some time. So Arjovsky and Botu revealed this property in their ICLR 2017 paper, and actually use that to justify using a Wasserstein distance rather than a phi divergence as a critic function for GANs. So I've just told you that KL is a catastrophically bad critic, and yet 10,000 GAN papers use KL or Jensen-Shannon or some other phi divergence. So evidently it can't be as bad as all that, because otherwise thousands of papers wouldn't have been published. So what explains this weird gap between what KL should be doing and what KL is actually doing? So what's interesting is that we should look a little bit more closely at how the phi divergence is being used as a critic function in GANs in practice. Okay, are we really using KL, or are we doing something else? So here is where we start exploring a little bit how KL is actually used. So here is our KL, expectation under Q of the phi of ratio P to Q. Now we're going to first play a little mathematical game, and we're going to rewrite this expression in terms of the solution of an optimization problem. So this phi star function is the dual of my original phi function. So the dual function is basically like the slope-intercept form of a function. What does that mean? That means if I have a function phi, if I input to the dual a slope of that function, then I can take a tangent line where the phi has that slope, and phi star returns the intercept of that tangent line. Okay, so basically phi star takes the slope, draws a tangent line to phi where it has that slope, computes the negative intercept. Okay, so and if phi is strictly convex, then the slope-intercept form uniquely characterizes phi, because the slope uniquely determines the intercept for a convex function, a strictly convex function. Okay, so if I use this slope-intercept form, this dual form of phi, and write this optimization problem, basically like I'm optimizing over the slope for every value of z, so for every value at which I evaluate this function, then I recover my original phi function. If for every z at which I'm evaluating phi, I solve for this slope, I use this slope-intercept form, and I maximize this difference here, then I recover my original function. So I haven't actually, achieved anything here. I've just written phi in an equivalent form using this dual. Okay, so what was the purpose of playing this game? Well, for the way that I've expressed my function here, I need to find a different f, a different slope for every value of z. And this can be an arbitrarily non-smooth function. But what if, rather than using an arbitrarily non-smooth function over z, I replace that with a smoother function? Then I'm not going to solve this optimization perfectly at every z. I'm going to get a lower bound. And that's what I've written here. So rather than using this arbitrarily non-smooth function class, I'm going to replace this with a smoother function class. What's interesting here is that you should be getting flashbacks to the integral probability metric. So this is not quite an integral probability metric, because it's not EP of f minus EQ of f, it's EP of f minus EQ of phi star of f. But it's nonetheless a difference in expectations evaluated over some well-behaved class of functions. So one might expect it to start drifting towards an integral probability metric in its behavior and drifting away from this phi divergence behavior. When is this bound tight? Well, the bound is tight when f is equal to the gradient of phi at p to q. Okay, so as long as the ratio of p to q is defined, then f diamond, so the f that maximizes this lower bound, is the derivative of phi evaluated at p on q. Okay. So this is this lower bound form of the phi divergence. Let's see how it applies to KL. Okay, so here is my KL. So log p on q, integral over p dz. Step one is to replace my phi with its dual form, and then to replace the f with the set of smooth f's. What I've done here, rather than using f as my parameterization of the dual form, I've used minus f plus 1. For a reason that's going to be apparent shortly, it'll give a more convenient form for the solution. Okay, so I've got this minus f plus 1, I've got the dual of minus f plus 1, and I get a lower bound here because I've restricted my f's to be smooth. Right? What is the f diamond that maximizes the lower bound? Well, the f diamond, using this minus f plus 1 parameterization, is the negative log ratio of p to q. Okay, so here is an example where p to q indeed have a well-defined ratio, And in green, I've plotted the F diamond, so the F that maximizes lower bound for these two Gaussians with different means. And you can see that the log ratio is a straight line. Okay, so that is the F that maximizes the lower bound. What's interesting about this function is that I'm plotting it here, on a log as a log ratio. But obviously, the ratio itself is going to blow up pretty severely. And so that's something that might perhaps concern you when you're computing the lower bound on the F divergence. So we'll return to that point. Okay, now I've got a difference in expectations under P and Q of, on one hand, F, on the other hand, e to the minus F. I can now compute these expectations using samples. So let's say I've got a sample of real bedrooms, a sample of fake bedrooms. I can just substitute these into my function, and then I can get an estimate of my lower bound on my KL from samples. Okay, and this is what I computed in practice. If I've got data, if I'm training again, I've got my real samples, I've got my fake samples, this is what my critic would return. Okay, so we call this a KL approximate because it's an approximation, lower bound estimator, or the KL divergence. The KL divergence sounds like the KL divergence, but it's actually something quite different. And this is what people actually use in GANs. Okay, so let's look at the topological properties of the KL. Okay, so one requirement that we might have is that when P and Q agree, we want our KL to be 0, right? If we get the answer right, we want our loss to be 0. And this is going to be true as long as the class of functions we use to compute our KL is rich enough. So remember, we've got this function class that parameterizes our lower bound. If these functions are rich enough, then they will be able to detect any difference in P and Q. In particular, let's say that we are on a compact domain, okay? Then I need to be, my H has to be dense in the space of continuous functions. So it needs to be arbitrarily close to continuous functions on this compact domain. If that is the case, then we can be sure that KL is 0 only when P and Q agree. So what is an example of a rich enough class of functions? The universal reproducing kernel Hilbert spaces are, by their construction, dense in the space of continuous functions. So these satisfy the requirement. For neural network classes, the span of these ReLU style functions, so these ReLU style functions, are affine transforms of my data, as long as these transforms are, sufficiently rich. So basically, like up to scaling, the class of transforms should be able to, I guess, recover any transform where W and B are in RD. These also are rich enough, okay? So this is like a one-layer neural net with a very rich class of linear transforms. If I take the span of all of these functions, that is rich enough as well to ensure that this is 0 only when P and Q are the same. Of course, this is the infinite set of all possible transforms, right? So like all sums of transforms of X plus B. So that's perhaps too rich a set of transforms to implement in practice, but you can approximate it using a very large neural net. So yeah. Okay, so this is one property. Like this tells us that our KL is 0 only when P and Q agree. Which is sort of part of the way there. Like it tells us that it's a useful loss. It's a loss at 0 only when P and Q agree. But remember from earlier, we had this sort of notion of a constructive or an unhelpful teacher. And a constructive teacher tells us that as Q approaches P, our loss function should drop to 0, should give helpful feedback. Now, this is a property that the KALE divergence has. So let's say that I have a sequence Qn of let's say fake bedroom samples. So my generator is generating a sequence of samples. It's getting closer and closer to the target distribution. Now, if these generated samples approach the target in weak convergence, in weak topology, then we have KALE going to 0. And conversely, when KALE goes to 0, that ensures that Q approaches P under the weak topology. So when Q converges weakly to P, then KALE is going to 0. So this is, a very helpful property because it's telling us that as Q gets closer to P, our KALE is going to drop. And it's not, it's not something like the original KL, which was infinite, 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 and then 0. Now, the proof idea relies on the fact that the KALE is in some sense in behaving closer to an integral probability metric than it does to a phi divergence. And so the property that it has basically takes the strength of the IPMs rather than the strength of the phi divergences. So remember earlier when I said that the lower bound has, for the purposes of training GANs, better properties than the phi divergences, that's this slide. All right, so here's our KALE, here's our variation lower bound, so which is minus FDP minus e to the minus FDQ plus 1. Here I'm going to do something very simple. I'm going to add and subtract the integral of f, okay? Integral of f dq, integral of f dq. So I haven't done anything very interesting here. But now I notice that I've got this term here, e to the minus f plus f minus 1. And if you do a little algebra, you'll notice that this is always non-negative. So I've got the integral of a non-negative term and I subtract it. Well, I can then get an upper bound by removing that term. And then I have an integral probability metric. Okay, so I have an IPM that upper bounds my KALE. Let's now say that my function class is Lipschitz with constant L in its inputs. Okay, so I've got a smooth function class. If that's the case, then I can in turn upper bound this by this Lipschitz constant times the Wasserstein 1. And I know that the Wasserstein 1 under weak convergence is going to go to 0. And so that goes to 0. Therefore, I sandwich my KALE, and that goes to 0 as well. So basically, because of this sort of similarity of KALE to an integral probability metric, I have the nice property that KALE is going to 0 if and only if Q converges weakly to P. And this is a nice property that KALE has, that the variational lower bound has, but which my original phi divergence didn't have. All right. So now let's go back to the toy illustration that I had earlier and look at the empirical properties of KALE. So here's my KALE, EP of f minus EQ e to the minus f plus 1. I'm going to use here a kernel class for my witnesses. So the H is going to be an RKHS class. And I'm going to penalize the norm of my function, which is going to ensure that I get a smooth function out. Okay. So we're going to call this the KALE smoothie. So let's look now at how the KALE smoothie performs. Here we see this for the blue and red, which are a little bit disjoint. And as red approaches blue, you can see that the KALE smoothie is dropping, right? So it's going from 0.18 to 0.12. So indeed, this is a constructive divergence measure. This is telling me that red is approaching blue. So this is a good thing. This is like, telling me that as a critic class, the KALEs, or the variational lower bounds, are actually helpful to me, are giving helpful feedback to my student. And yeah. So there is, of course, no free lunch. And using the variational lower bound with a smooth function can also cause some pathologies. One of the pathologies, a notorious one in GANs, is relating to mode collapse. So here is a toy example illustrating the mode collapse problem and why it is that a KALE might not penalize mode collapse sufficiently. Okay, so I have a very simple toy example. I have two Gaussians. They share the mean, but one has variance which is different to the other. Okay, so my red has variance which is narrower than my blue. And if I have mode collapse, that means that the red has variance which is much, much narrower than my blue, right? Because basically my red, my generator, is focusing on the mode rather than trying to cover the support of my blue. Now, because these are two Gaussians, I can compute the KALE, the real KALE, in closed form, and that's what I've done on this axis here. And obviously, as I mode collapse, my KALE is going up, all right? And that's what this green line is. It's basically like the green line is the one-to-one mapping between KALE and where it should, where it should be. Now, on the y-axis here, I have my variational lower bound, my KALE, okay? And what I'm noticing here is this orange curve, which is that as KALE goes up, my KALE, my variational lower bound, is not going up nearly enough. So I'm not penalizing mode collapse as much as I should be. And the reason for that is that I need to approximate the log ratio P to Q using my smooth functions. But this log ratio is going to blow up like crazy when I have severe mode collapse. and I will not be able to approximate this log ratio with a smooth function when I have severe mode collapse. So my lower bound gets worse and worse and worse the more that mode collapse occurs, and therefore my KALE is going to get, is going to diverge more and more from my true KALE. So this is in a sense what you pay by using a variational lower bound rather than the original KALE in this instance. All right, so that's everything I want to say about critic functions. Now let's go back to the modeling problem. Okay, there's a question. What if you combine integral probability metrics and p-divergences with a critic? Yeah, so I think in a sense, like the KALE borrows properties from MMD. And so in a way, what it's doing is it's sort of like moving away from the p-divergence form and towards an IPM form. If your goal is to train a GAN, GANs have been trained, I think, very successfully with IPMs. Like there's Wasserstein GAN, WGAN GP, MMD GAN, and so on. If your goal is only to improve your generator, I would say that it's not obvious why you would use a phi divergence or a variational lower bound on a phi divergence which approaches an IPM or an IPM. However, and this talk could have been about MMD GANs. Like I've given talks about MMD GANs where I've told everyone that they're wonderful. The reason for using a KALE though is because the phi divergence form lends itself to being used to improve the samples from the generator in an end-to-end model. And that's what I'm going to talk about next. So the phi divergence form, basically because of the relation between KL and likelihood, the phi divergence form is the form most convenient to use if I want to incorporate my critic and my generator into a single model to generate samples. Does that make sense, Christopher? Great. Okay, so let's return to our original cartoon. We've got our generator, it generates fake dogs. We've got our critic. The critic takes a set of fake dogs, set of real dogs, compares the two, gives feedback to the student, and this cycle continues until an equilibrium is reached. All right, and then what happens? Well, what happens then is that we take the teacher, we throw it in the trash, and then we send the student out in the world to generate samples on their own. Okay, and this is something that we do even though it may be that the critic still has information about differences that remain between my real and fake samples. So the critic knows that the student is wrong, but the critic has been thrown away. And so, the information that the critic has been lost. And every GAN that is trained trains both a critic and a student. And it seems crazy to take, all of the work used to train this critic and then throw the critic away. Why not use the critic to improve the samples from the model? And as you would expect, that's always going to improve the model as long as the critic has some useful information. Okay, so let's first of all remind ourselves what it is that the student is doing. Okay, the student is taking some low dimensional noise, and then it's pushing it through a set of transforms to generate images, let's say, in a much higher dimensional space. But because the input noise is low dimensional, what's coming out of the student is occupying, in some sense, a submanifold in this high dimensional space. Like the set of legitimate bedrooms is a very small subset of the total pixel space in whatever the dimension of the image is. Okay, so this is what the student is doing. Okay, so I'm now going to illustrate, bearing in mind that this is what the student is doing, and this is the task, which is to take like some low dimensional noise source. And then to use that to generate, let's say, target samples in a higher dimensional space. Let's sort of take this and make it a, as low dimensional a cartoon as we can get away with. So here is a very simple task, okay? The target distribution here is P, and I've plotted samples from P here. What you're going to see is two things. So first of all, it's in a 2D space, but it's occupying a one-dimensional submanifold in that 2D space, all right? And this is to capture this idea that generally for GANs, even though we're in a high-dimensional space, we want to generate samples in a very low-dimensional support in that high-dimensional space, like images within pixel space, okay? Second property that we want to capture is that the mass is non-uniform. So maybe here, this is a much less likely bedroom. And here, this is a much more likely bedroom. So even though we're generating samples on this submanifold in this high-dimensional space, we want to make more samples, say, here and here, and fewer samples here in the middle. So this is our target task. And I'm sort of expressing that in this simple form here. So Z is a uniform 0, 1, one-dimensional variable. Z tilde is a distortion of that, where I put more mass towards the ends. And then X takes that one-dimensional line with more mass on the end and turns it into this sort of decaying sinusoid in 2D space. Okay, so that's what this G star is doing. So this is my target. Let's say that I want to generate samples that match that target. One way that I could do this is to use energy-based model. Okay, energy-based models are very well known. They've been around for decades. They're very popular. And they basically take the form of P of X proportional to some exponential of e to the minus exponential of minus e of x. Okay, where e is an energy function. And here I've used basically like a very good energy function, which is a Gaussian blur, let's say, or a quadratic proximity function around my target, G, where G is actually the correct answer. Okay. But what you'll notice about these energy functions is that they need to have density with respect to the Lebesgue measure. So basically, P of X has to be a density in 2 dimensions. It cannot be a one-dimensional submanifold in a 2D space, right? An energy function like this P of X, it needs to have density with respect to Lebesgue on whatever the dimension of X is. Okay, and that's a problem because like I want a one-dimensional submanifold. But these energy-based models will always give me like a blurry density around that target by construction, by the definition of an energy-based model. So if I'm using an energy-based model to generate bedrooms, I'm going to get blurry bedrooms. If I use it to generate dogs, I get blurry dogs, blurry faces, etc. So the human visual cortex is very unforgiving of blurry images. So obviously, a state-of-the-art GAN is not going to be a GAN that generates blurry faces. Let's now see what a GAN might be doing. So here I'm using a GAN to generate targets, and I've in some sense used a, shall we say, like a simple generator here, such that the generator is able to capture the support of my distribution, but isn't able to capture variation of mass on that support. So basically, like it's taking my uniform distribution, and it's only like I'm by construction, I'm only allowing it to distort let's say the coordinates that I place this mass on, but I'm not allowing it to place more mass at different parts of the support. Okay, so what this is doing is it's getting the support right, but it's not getting the mass right. If this is the case, then what I might want to do is to reweight the output of my GAN generator using an energy function such that I capture not only the support, but also the mass on that support. Okay, so somehow I would like to learn this energy function to take the support of my GAN, which I've assumed in this example that I'm able to get correctly, but I want to then change the amount of mass placed on that support such that I place more mass at the ends as my target requires and less mass in the middle. And a generalized energy-based model is going to use the critic function to do that reweighting, to achieve that reweighting. Are there any questions about that before I go on? About this toy example? So just to recap, my target function looks like this. So it's on a low dimensional support in the high dimensional space, and the placement of mass on that support is non-uniform. Energy-based models have to have a density with respect to the ambient space, so have to have density with respect to the Lebesgue on here R2. In this example, my GAN has sufficient capacity to place mass, in the right support, but it still hasn't quite matched the amount of mass on that support. So it's not placing enough mass on the ends, and it's placing too much mass in the middle. What I want to then do is to use an energy function to reweight the mass such that I get the mass matching my target. And the critic function, as we're going to see, is going to give me this energy function. So this is the sense in which the critic is going to improve what the generator does. The critic cannot tell me where to place mass, but what the critic can do, as we're going to see, the critic cannot tell me where to place support. Okay, support is chosen by the generator. But what the critic can do is to improve the placement of mass on the support. That is what the critic is going to buy me. Okay, energy-based model causes, yeah. Right, so basically like the GAN model is not going to be blurry because it's, it's able to place low dimensional support in a high dimensional space. But what it might do, and where we're going to use the energy, like let's say that the critic function contains information that tells us that the GAN and the target still don't quite match. One of the reasons for that mismatch is that it could be that the GAN is placing too much mass on some parts of the support and too little mass on other parts. And what we're going to see is that the critic function will give us an energy function, which will allow us to do importance weighting on that support. So allow us to place more mass at the ends in this case and less mass in the middle. Does that make sense, John? Great. Any other questions before I go on? So I've sort of left a little mystery hanging here. I've said that the critic function is going to give us this energy function, this importance weighting, which is going to take the incorrect weighting of the mass from my generator and is going to refine it, is going to place more mass on the ends. Okay, now let's see how it does that. Oh, there is a question.
I have a question. How can we be sure that the subspace is actually true? So isn't it by construction that our data lives in a low dimensional subspace?
That is a very good question. So I've sort of left a few things unspoken here. So one is, in this case, my generator, it's a very simple example. It's in 2D. I can see how many dimensions the submanifold occupies, and I can construct it correctly. Now, if I'm doing bedrooms in, however many dimensions my pixel space is, what is the dimension of my submanifold of valid bedrooms in pixel space? That's a very deep question and one that I cannot, I think, correctly answer. So at that point, I think this becomes, shall we say, a graduate student descent problem. We try different dimensions of generating noise. We try different architectures of generator networks until we get, images that are satisfactory to us. So, absolutely, it's the case. I may have a GAN which is generating support too low dimensional. The energy function will not be able to repair that. The energy function can change the mass I place on the support, but it cannot change the support. Mm-hmm. Now, it may conversely be that the GAN has support which is too high dimensional. Here, the energy function might help me because what it might do is to some extent, to assist me in focusing my mass on the regions where samples are more likely.
Okay, thanks.
Yep. Any other questions before I go on? All right. Okay, so I've said, but I haven't yet explained, that the energy function is going to be given to me by my critic. Let's see a little bit why that is. Okay. So first of all, I need to express in mathematics what it is that I expressed verbally in the last couple of slides, which is how does one define a generalized energy-based model? Okay, so a generalized energy-based model is something that combines a generator, which places mass, and an energy function, which reweights that mass, which importance weights the mass. All right. So Q, my model, has two things: generator B theta, energy function, importance weighting function, E. Let's first see what the generator does. The generator takes a low dimensional noise, passes it through a set of convolutions, some mapping, parameterized by theta, and outputs a sample, a fake bedroom, let's say. Okay. Now, what happens after that? Well, my energy function, which does the importance weighting of my generator samples, takes the form e to the minus x. And so basically my end-to-end model will take x generated through this network and then weighted by this function e to the minus x divided by this normalizing constant, which is e to the minus x, integrated over the measure from my generator. Okay, so that is what this FQE is. My end-to-end model takes my generator samples, weights them by e to the minus energy. And E is the energy function class, which we have to learn. Okay. Now, if Q were to have density with respect to the VEG on X, so if Q is supported over the entire domain X, then this is just an energy-based model, standard energy-based model. It's been studied like for decades. We don't have to worry about that. But this is not the case we're interested in. We're interested in the case where the support of Q is on a much lower dimensional submanifold, say, in this high dimensional space. Okay, so that is the case that we describe here, and that's why we use this phrase, generalized energy-based models. Okay, how do we fit a generalized energy-based model? Well, we fit it using a generalized log likelihood. Okay, so we just take the log of our model and we integrate it over our data distribution. What's interesting though is that, well, okay, two things. First of all, when KL is well defined, so when the ratio of P to Q is well defined, this is the, I think, well-known Donska-Varidan lower bound on the KL, okay, which is tight when the energy function is the negative log ratio of P to Q. So if P and Q have densities with respect to the VEG on the ambient domain, and if the ratio of P to Q is well defined, so if the support of P is contained within the support of Q, then this is a lower bound on the KL divergence, which is tight as soon as my energy function hits the ratio of P to Q, which, surprise, that's the importance weighting ratio, okay? However, as I emphasize, this is not the case we care about. P and Q might not even have overlapping support. P might not have a density, Q might not have a density. However, the generalized log likelihood is still well defined. I can still take the expected log of this function f, and I can still optimize that with respect to my parameters e. Okay, so the important thing to emphasize here is that even when P and Q don't have densities, even when P and Q don't have overlapping support, this generalized log likelihood is still well defined and I can still optimize it. Okay, so this is the criterion that I'm going to be using to optimize my E. All right. So let's now explore this generalized log likelihood a little bit further. Here's my generalized log likelihood, log f dp, okay, which is minus e dp minus log z qe. Let's say that I'm trying to use that to learn my energy function. All right, here is a way not to do it. Okay, a way not to do it is I take my mini batches of samples from P and Q, I compute the log z, the log normalizer, from the mini batch of my Q samples, and then I do gradient descent. So why wouldn't this be a good way to do it? The reason is that I would get then a pretty high variance, as well as, of course, biased estimate of my log partition function, of my log normalizer. Because I'd take like a little sample from my generator each time, and I'd compute this, and then I'd recompute it, and then I'd recompute it, and then I'd recompute it every time I take a mini batch of P and Q samples. So obviously, like, this is going to be noisy. So here we use a rather fun trick, which is that we can lower bound the log z using this expression here. Okay, and this lower bound becomes tight when c hits the correct answer at log z, my log normalizer. So again, like, it seems first a little bit counterintuitive, like, why would I replace log z with a lower bound? Well, it turns out that then I have a way of optimizing where I'm able to like update c sequentially over multiple mini batches. Okay, so here is my generalized log likelihood where I've used this lower bound. So I've got e to the minus e plus c dp minus e to the minus e plus c dq plus 1. And what I would then do is, for every mini batch P and Q, I would update my parameters of my E and I would update my C. And so I'd have this amortized update of C where every mini batch I improve on my estimate of my C, and then I get a much lower variance, much more accurate estimate of my log Z than I would if I just recomputed it each time. Are there questions about that? Okay, so this is how we learn the energy function in a much lower variance and more reliable way than we would if we were naive about learning the energy function using the generalized log likelihood. Okay, and so now comes the grand reveal for the talk, which is that this generalized log likelihood using this E plus C formulation is the KALE. So this is how the critic function is used as part of my model. Okay, so this is the KALE divergence between P and Q when I use as my function class a set of energies and a constant, where the constant captures my log normalizer and the energies are, trying to approximate my ratio of P to Q. Okay, so if I have a critic function and I use this class of functions E plus R to optimize my critic, then I can incorporate that critic function into my generative model as an energy function, as an importance weighting function to improve my samples. Yeah, so basically, you will be able to sort of page back on the slides when you have them online, but you'll notice that you've got, expectation of a function dp, e to minus a function dq plus 1, which is indeed the KALE, the variational lower bound on the KL. And so now we understand how the energy function relates to the critic. The energy function is effectively the witness function of the critic when we use the KALE divergence. Questions about that before I go on? Okay. So indeed, jointly maximizing this gives the energy and the corresponding estimate of the log partition function. Okay. The thing that I'm not going to talk too much about is how to learn the generator, because that's fairly standard. I'll just spend a very short time on that. Remember that the generator takes a noise, a low dimensional noise, pushes it through some, let's say, convolutional filters and gets out, say, images of bedrooms in a much higher dimensional space. Okay. Now, let's say that I've learned my energy function, and this is my KALE, my variational lower bound on KL with that learned energy function. Okay, then the derivative of KL with respect to my generator parameters is given by this expression here, where the E star is the optimal energy function. So if I train my my critic to convergence and I use that E star, then I can compute an unbiased estimate of my derivative of my K. Now, of course, maybe I don't want to train my energy to convergence, but then I get an approximation to this derivative. This requires some smoothness assumptions. They look a little bit technical here, but they actually make a lot of sense. So first of all, my energy function has to be smooth with respect to its inputs. Pretty obvious. Second, my B function has to be smooth with respect to its parameters, because I'm taking the derivative with respect to the parameters. So those are the sort of two key assumptions. And both of these make sense. Like, it's not a surprise. And if that's the case, then I get this derivative of my KALE with respect to my parameters of my generator. And I can then use that to optimize my generator parameters. What I do in practice, I alternate optimize generator, critic, generator, critic. I optimize my critic a few more iterations because I want my energy function to be reasonably accurate when I compute the derivative of my K for my generator. Okay, finally, I've trained my model. I want to draw samples from it. Now, for GAN, it's super easy to draw samples, right? I take my noise, I push it through my generator, I get out a sample, done. Now I've got this energy-based function, this importance weighting function. Drawing samples becomes a little bit harder, but not that much harder, okay? So here's what my model would be doing, okay? I take my sample, I push it through my generator network, I get my bedroom, and then my density is a reweighting of that, right? An importance weighting of that. Now I could do something like incredibly naive and terrible idea like rejection sampling, but we're not going to do that. We're going to do something a bit smarter than that. What will motivate this smarter approach is to think about what the posterior over the latent space of my generator looks like. I want a posterior distribution over Z, which incorporates this energy function, okay? So I'm placing more mass for certain code words in my latent space and less mass for other code words. Okay, the way that I can understand that is by looking at the expectation of a function g under my model. Okay, if I have a function g, I take its expectation under q, then it's g of like z pushed through v, and then this importance weighting. So from this, I understand what my posterior looks like. My posterior looks like the prior over z times this f evaluated at b of z. And so that gives me a posterior over my code distribution. If I use then Hamiltonian Monte Carlo to sample from that posterior, and then I push those samples, then I will be sampling from values of z, which will give me better quality images after they go through B. So I use this posterior, I sample from it, I take these special z's in the right part of the space, I push those through my generator, and then I get way better samples than I would if I just pushed random samples from my original eta distribution. So this is how we sample from the model. Right. So I think I'm coming to the end of my time, so I'm just going to show, of course, it's a machine learning talk, so there have to be some pictures. So here are some samples from the generalized energy-based model using a kinetic Langevin algorithm. So this is quite related to HMC. We're running the model at low temperatures. What that means is that we're focusing at high probability regions in my model space. The reason for that is that these are the least blurry images, okay? And what you can see is that as we run our sampler, the path brings us to, let's say, regions of the image space, which result in sharp outputs, which result in good quality images. Okay, the next slide here is evidence for a claim I made at the start of the talk that using the critic, or more specifically the energy function from the critic, improves the quality of the samples over throwing it away. And that makes sense, right? Because the critic knows where it is that your generator is not placing enough mass or placing too much mass, and it adapts that by this importance weighting. Okay, so basically lower is better. This is for 4 different image data sets. And you can see that like 100 is what you would get if you just use a generator, nothing else. These orange bars here are what we get using our method, which incorporates the energy function. These other approaches are approaches that are not based on energy-based models, but also try to use the critic to improve the generator samples. But we believe that using this energy-based approach and incorporating the critic function into an energy-based model is a better approach to improve the samples. Finally, you can run the sampler at lower friction, which allows it to jump from mode to mode. And this is the trace of the sampler when we do that. And you can see that the sampler is going from a car to like a wildlife thing to a different car, or from a horse to a view of the sea, I guess, to a donkey, and so on. So the sampler is sort of like, one I guess perhaps question one might have about this model is, does the model just get stuck on a single mode, or does it explore the space? And the answer is that if you choose your sampler well, it does explore the space. It goes from image to image and generates samples that span the space of the samples from the input. So I think that's a good time to stop for questions. So notwithstanding that there were very few kernels in this talk, I will nonetheless advertise kernel beer. Thank you.
Yeah, I have one more question. Couldn't your sampler produce like adversarial attacks for the critic? Would that do any harm?
Oh, actually, I forgot to show that slide. But so when you say adversarial attack for the critic, so what you perhaps, if I understand your question correctly, does that mean a sample in a region of the space where the critic believes that the importance weight is very low, which is to say that the sample is in a region of the space where it's very unlikely that a true sample would occur? Is that right?
Yeah, like a critic is a classifier in the space of images, right? And
yep.
you may, like, if if you produce small distortions in the space of images, you may fool a classifier which is not robust against these types of attacks. Could that happen, or is it due to the subspace that this is prevented?
Yeah, so I think I think it can happen with the function classes used. So obviously, you could find in your critic, you're absolutely right. You can think of a critic as a classifier because it's taking the ratio of class A to class B, and you can imagine, given a fixed critic, moving in a direction which is in a sense misleading to your critic. I think the way that a GAN is trained might mean that jointly the energy function and generator don't explore that space. So the energy function is trying to minimize the KALE, the variational lower bound. The critic is trying to maximize its KALE, is trying to find regions of the space where the target and distribution and the generator distribution are most in disagreement. So in a way, like neither the generator nor the critic has an interest in, or rather, let's say that the generator has no interest in producing samples that are adversarial to the critic in a way. Or, okay, maybe that's actually slightly wrong. So I could say that my generator could place examples in a place which was adversarial to my critic in its current form. But then my critic would win by adjusting its function to detect those adversarial examples.
Yeah, no, what I mean, the model would be completely trained, and now if an adversarial example would have a low energy for the critic, then you would probably, with higher probability, end up with a sample like that.
So you're sort of saying, like, if I then take a generator which is placing mass in points of space where my energy function is inaccurate.
Maybe.
Yeah, no, absolutely. No, so I should be very clear about that. No, this would break it for sure. So if I took, let's say, my energy function is only good on the support that the generator has allowed it to see. So now let's say that I take another generator, and my generator is like setting out to break my energy function. And I can then basically move to a part of the space where the energy function is very poor. Yeah, absolutely. No, so, the energy function has to work in pairs with the generator on which it was trained. And I could for sure find an adversarial generator which would place samples where my energy function is terrible.
Yeah,
absolutely. And that would be that would just break it completely for sure. Yeah.
Okay, got it. Thanks.
Thanks so much. Any further?
Oh, I see a raised hand by AHCENE.
Asan, yes, Asan. Okay, go ahead.
Yeah, okay. So Arthur, first, thanks a lot for the great talk. Okay, if I understand well, what you are doing is you learn where it's best to sample, right? So my question, maybe I think it's a bit related with what Roland just asked, but it's also related with his talk this morning. How can you assure then diversity in your output? Maybe there are some areas where the energy is not good, but you might still get very good samples, and maybe you also. Well, how can you be sure you will generate pictures that are good, but that are still far from the training data? You see what I mean?
Yeah, no, so this is a very good question, and I think it's somewhat of an open question even, in the sense that one limitation of this whole talk is that we rely on the generator architecture to place the mass. Okay, the energy function, given where the generator has placed mass, the energy function can put more or less weight. However, if let's say that there is some part of the space up here where the generator should have put mass and didn't, I can never recover that. Okay, so the problem of mode collapse isn't solved by the energy model. The model is sort of saying, given that I've got the support correct, I will refine the mass on the support. I think so where like I think there is some very interesting work to be done is in perhaps designing generators to not drop modes. And there are multiple reasons why modes might be dropped. So one nice example is that let's say I have a data distribution with two classes, one with a very narrow mode, one with a very broad mode. It may be that my generator says, well, I know an easy answer to this problem. I focus all my generating power on the narrow mode and I throw away everything from the broad mode and I win. Great. And that, that's something you actually see a lot in practice. So that is my cause for pessimism. My cause for hope is that using these generalized energy-based models might allow us to use generators which are a little bit lazier than one needs for GAN. What I mean by that is that they are going to place mass on a much broader distribution than the target, and then rely downstream on the energy function to refine that mass. So basically, like in training such models, we would architect them differently to a GAN because we would allow the generator to place mass very broadly. And then we'd rely on our critic function to basically throw away parts of the space which don't matter. And this is what our critic function can do. Like this is what it is good at. That I think is a direction to explore. Like it's because the way that GAN architectures are being chosen, they have tended to be very conservative in placing mass. So I don't yet know what an energy-based model with such a broadly supported generator would look like. But I think this is a very interesting direction to try.
So thank you so much. We have a quick question on the temperature in the energy. Mm-hmm. If this affects.
Yes, very good question. So, sampler tuning, is an art form. So the Bayesians have endless, shall we say, ceremonies and mechanisms for tuning these samplers. One thing that so in a sense, like there are two knobs that we care most about. So one is temperature, one is friction. So one can think of a Hamiltonian Monte Carlo sampler as, let's say, a surface in like a sort of topological surface where you flick a little ball bearing, a little steel ball, and it zooms around the surface. And the flick that you give it is the kinetic energy. Now you can adjust certain parameters. So one is the temperature, so how steep these peaks are in the surface. The second thing is the friction with which the ball bearing is sort of slowed as it rolls around on this surface. And that will determine where on the surface you explore. What we found for the purpose of getting very good quality images is that it really helps to have the temperature low, which is to say that this topological surface should have very, very deep valleys. Which means that the ball bearing spends a lot of time at the very peaks of these surfaces, which are visually the most appealing images. Now, if my goal instead was to explore the support of my images, maybe I would actually want to increase my temperature a bit to ensure that my ball bearing isn't stuck at these modes, but spends time going from mode to mode. Alternatively, as we've shown here, we can achieve a similar result by dropping the friction. So that means I go from mode to mode. However, I'm still not really exploring the support so much because I'm still spending most of my time at the very lowest points of my energy surface. I think here, in some sense, the answer is like, what is your goal? Is it to explore the support? Is it to generate good quality images? Then you should sort of be aware of how your sampler operates, and you should, as a user, adjust the parameters to give the answer that it is that you're searching for.
Yeah, super interesting. So your talk is so interesting. It raises a lot of questions. We have to round up pretty soon. I just had a small comment I wanted to ask you about. So if I understood correctly, you started out with the divergence measures, and you showed us these nice connections. You took the KALE and you showed us the approximation, the KALE. And then going into the energy-based models, you showed that kind of when you wanted to do the optimization, you ended up with the KALE once again, and then you could use that.
Yep.
So you went from the energy-based model, and you came to the KALE, and you showed that this was a sensible choice. But the KALE, you could also have other approximations to divergence measures. So could you go the other way around and like reverse the path and say that, okay, I want to optimize by something else than KALE, and it would give me a different kind of energy function to start with? Would that make sense?
This is absolutely does, and this is why I'm quite embarrassing that I accidentally skipped over my summary slide. So here I really want to emphasize this is a very good paper by the group at Mila, the organic secretly an energy-based model, and they absolutely explore the question that you're asking. In fact, our papers came out within 2 days of each other on arXiv, and we cite each other. I think these papers fit extremely well together. So this paper again uses this notion of an energy and uses Hamiltonian Monte Carlo to sample from the end-to-end model. However, they do exactly as you say. They train the energy function using, in their case, either Jensen-Shannon, or they also explore, and this is quite an interesting, a way to sort of derive an energy function from an integral probability metric. So they also explore a bit that direction, which we don't at all. So, the short answer is absolutely, like, there are many, many ways to get an energy function for a generalized energy-based model. This paper does another one, and I really encourage everyone to read it because that is a great, I think, complement to the KALE approach that we use. Yeah.
Okay, thank you. That's very, very interesting. So, okay, we have to stop for now. I would like to go on for a long time still, but